We live on a tiny, spinning rock, hurtling through the dark at 67,000 miles per hour. Yet, simply reaching our nearest planetary neighbor takes months of precision flying. The farthest destinations in our solar system require over a decade. The time it takes is deeply counterintuitive. If you think space travel is simply about covering distance, you are absolutely wrong. The true enemy is a brutal mathematical triangle of velocity, gravity, and orbital mechanics. We are going to journey through our solar system, planet by planet, and reveal the exact travel times, from Venus in just over a month to Neptune in a grueling 12 years. We will also uncover the incredible physics that allows us to travel at all, and the invisible walls of radiation and propulsion limits that keep us trapped. We will also reveal the ultimate secret to breaking every speed record and cutting years off a deep space mission, a trick involving Jupiter that saved nearly a decade of travel time. If discovery is your thing, subscribe to Stellify Science and turn on notifications so you never miss what the universe reveals next. The journey begins with Venus, a planet that, at its nearest point, floats just 38 million miles away. Logic suggests this should be an easy, fast target, but space doesn't work in straight lines. NASA's Mariner 2 mission took 3.5 months to reach Venus in 1962, covering a distance far greater than the initial gap. The reason is pure orbital physics. You are not just traveling 38 million miles. You are trying to intercept a target that is moving at breakneck speed. Earth orbits the Sun at 67,000 km/h, while Venus races even faster at 78,000 km/h. It is the cosmic equivalent of throwing a ball from one speeding train to another, moving on a different track in a different direction. You must perfectly calculate the launch window, so your spacecraft and the target arrive at the same place, at the exact same moment. Modern spacecraft, using optimized trajectories, need roughly 32 days minimum to reach Venus. The Parker Solar Probe, one of our fastest vehicles ever built, still requires painstaking trajectory planning, not just to reach Venus, but to use its gravity for a slingshot maneuver. Missing the launch window, which opens when Earth and Venus align properly, means waiting months for another chance to even attempt the journey. The journey is an exercise in complex trade-offs. The spacecraft must slow down enough to be captured by Venus's gravity, or it will simply fly past into deep space. Chemical rockets can only carry so much fuel, making every single calculation of velocity and deceleration absolutely critical. The margin for error on a Venus mission is close to zero. What makes Venus missions particularly brutal is the heat. As the spacecraft approaches, solar radiation intensifies dramatically. Venus itself radiates scorching temperatures from its thick, dense atmosphere. Instruments must survive conditions that would destroy normal electronics in seconds. The surface pressure equals being half a mile underwater on Earth, and the clouds contain sulfuric acid. The Soviet Venera landers survived on the surface for barely 2 hours before the planet crushed and dissolved them. Those precious minutes provided us with images of a hellish landscape. Flat rocks, an orange sky, and crushing, absolute silence. The 32-day journey represents our absolute best-case scenario, using current chemical propulsion. Future nuclear thermal rockets could potentially cut this time significantly, perhaps reducing the trip to under 3 weeks. But that technology remains years away from being a reality. For now, we are stuck with month-long voyages to our closest planetary neighbor. Understanding Venus matters deeply, as it started very much like Earth, with a similar size, composition, and distance from the Sun. Yet, somewhere in its history, Venus transformed into an inferno. Its oceans boiling away, and its atmosphere becoming poisonous. Learning what went wrong there is essential to understanding what could happen here. But if you think 32 days sounds challenging, wait until you hear about the closest planet to the Sun. Mercury sits even nearer to Earth than Venus at certain times. At its closest approach, the distance shrinks to just 48 million miles. Logic suggests this tiny, fast-moving world should be easier and faster to reach than Venus. That logic is catastrophically wrong, and it reveals the first great paradox of space travel. NASA's Messenger probe launched in August 2004, but it did not finally enter Mercury's orbit until March 2011. That is 6.5 years to reach a planet closer to us than Mars. This seems impossible until you understand the nightmare of the Sun's gravity well. Mercury screams around the Sun at 107,000 km, making it the fastest planet in our solar system. Catching up to it is hard enough, but slowing down enough to enter its orbit is nearly impossible. This is because the Sun's gravity well is incredibly deep, constantly accelerating any incoming spacecraft. Messenger basically spiraled inward over 6 years, covering nearly 5 billion miles, and slowly bleeding off velocity bit by bit. Engineers had to calculate every maneuver years in advance. A single mistake would have sent Messenger either into the Sun or spiraling out into deep space. There were absolutely no second chances. During its 3 Mercury flybys, the probe collected incredible data, including photographing 95% of the surface. Scientists discovered water ice in permanently shadowed craters near the poles, water on the closest planet to the Sun. This discovery changed everything we thought we knew about Mercury. The planet itself is an enigma, with temperatures that swing from 800 degrees Fahrenheit in daylight to minus 300 degrees at night, the largest temperature variation in the entire solar system. Even with the aid of modern technology, Mercury remains brutally difficult to reach. Engineers will tell you it actually takes more energy to reach Mercury than it does to reach Pluto. This is the great paradox. The tyranny of the Sun's gravity well makes the closest planet the hardest target. Future missions face the same challenge. Bepi Colombo, a joint European and Japanese mission, launched in October 2018 and will not reach Mercury orbit until December 2025. A grueling 7-year journey. The spacecraft is using 1 Earth flyby, 2 Venus flybys, and 6 Mercury flybys to gradually slow itself down. Chemical propulsion hits its absolute limits here, demanding patience measured not in months, but in years. This counterintuitive reality teaches us a profound lesson. In space, distance means less than velocity and gravity. The easiest targets are not always the closest ones. Sometimes the farthest destinations are more accessible than our nearest neighbors. But there is one planet we visit constantly, one world where dozens of our robots currently work: Mars. The journey to Mars, the current destination of human ambition, has become almost routine, yet it still demands 7 months of precision flying. At its closest approach, Mars sits 34 million miles away, seemingly manageable until you factor in the waiting. Every Mars mission takes 6 to 9 months using current chemical propulsion, depending on the alignment. NASA's Perseverance rover, for example, launched on July 30th, 2020, and landed on February 18, 2021, 7 months of cruise through the interplanetary void. But the travel time is not the worst part. Launch windows to Mars only open every 26 months. Miss your window, and you wait over 2 years for another chance. This long wait occurs because Earth and Mars orbit the Sun at different speeds. Alignment is everything. Launch at the wrong time, and your spacecraft would need vastly more fuel. or simply could not reach Mars at all. The 7-month cruise phase is deceptively dangerous. Spacecraft coast through interplanetary space at roughly 24,000 km, and engineers must monitor systems constantly. Communication delays stretch to 20 minutes one way when Mars is distant. If something breaks, the spacecraft must attempt to fix itself before ground control even knows there is a problem. Radiation bombardment is a non-stop, confirmed concern for NASA engineers planning human missions. Cosmic rays slam through the hull, and solar flares erupt unpredictably. Astronauts would absorb dangerous radiation doses during a 7-month journey, and longer trips mean exponentially more exposure. This translates directly to a higher cancer risk and potential nervous system damage. The psychological toll is equally brutal. Imagine 7 months in a small capsule, with no fresh air or open spaces, watching Earth shrink to a tiny blue dot. Crew members would need extraordinary mental resilience to handle the absolute isolation. Entry, descent, and landing is the most terrifying phase, often called the 7 minutes of terror. The spacecraft hits the thin Martian atmosphere, traveling at 12,000 km, and must slow to zero and land softly. Everything happens too fast for human control. The vehicle executes pre-programmed commands perfectly, or it crashes. Current Mars missions use chemical rockets exclusively, and the 7-month travel time is optimized. Engineers have refined these trajectories over decades. Dozens of successful missions have proven the route works, but 7 months is still brutally long for human missions. NASA aims to send astronauts to Mars in the 2030s. Those crews would spend 7 months traveling there, over a year on the surface, waiting for the return alignment, and then 7 months coming home. A nearly 3-year total duration pushes human endurance to its absolute limit. The stakes are enormous. Mars once had liquid water, with rivers carving valleys and lakes filling basins. Then something changed. The atmosphere thinned, and the water vanished. Understanding why Mars died could teach us how to keep Earth alive. But here is the thing that haunts mission planners. This 7-month trip is only possible because we are using the fastest chemical rockets we can build. If we want to go farther, to the outer planets, the journey times become almost unthinkable unless we find a better way to move through space. Fortunately, we found something better, something that broke every speed record: the Jupiter slingshot. On January 19, 2006, a rocket launched carrying a probe the size of a grand piano named New Horizons. It was heading to Pluto, and it was in a hurry. New Horizons left Earth faster than any spacecraft before it, reaching 36,000 km right out of the gate. For context, the International Space Station orbits at 17,000 km. Pluto sits roughly 3 billion miles from Earth when closest. Using conventional cruise speeds, the journey would take decades. Voyager took 12 years just to reach Neptune, and Pluto orbits another billion miles beyond that. The team needed a different approach, and the key was gravity. The probe flew past Jupiter just 13 months after launch. This was not merely a bonus science opportunity. Jupiter provided a massive gravity assist that boosted New Horizons even faster. This is the trick that saved years of travel. The spacecraft emerged from the encounter, traveling at an incredible 51,000 temp. That is 14 miles per second. Blink your eyes, and it has crossed the length of Manhattan. Even with that record-breaking speed, the journey to Pluto still took 9.5 years. 9.5 years to reach a world we could barely see through telescopes. The probe spent most of that time in a hibernation mode to preserve its systems, waking only periodically to check instruments and make tiny course corrections. On July 14, 2015, New Horizons screamed past Pluto at 30,000 mph. The flyby lasted just minutes, with every instrument firing simultaneously. Cameras photographed the heart-shaped Tombaugh Regio, and spectrometers analyzed the thin atmosphere. Then it was over. The spacecraft could not slow down, could not orbit, and carried all that velocity out into the Kuiper Belt. The flyby revealed Pluto as a geologically active world, with mountains made of water ice, glaciers of frozen nitrogen, and possible subsurface oceans. It was not a dead, frozen rock. 9.5 years is a long time, but not impossible. The key was launching fast and using Jupiter's gravity boost. Without that slingshot, New Horizons would have taken decades longer. This mission showed us what maximum speed looks like with chemical rockets and a single, well-placed gravity assist. But even that incredible velocity took nearly a decade to reach Pluto. If we want to go faster and farther, we need fundamentally different technology, or we need to use gravity in ways that seem almost like cheating. This technique, the gravity assist, turns planets into cosmic accelerators. The concept is simple, but the execution is terrifyingly precise. Imagine a spacecraft approaching a massive planet that is moving through space at enormous speed. As the probe falls toward the planet, gravity pulls it faster and faster. The spacecraft whips around the planet and emerges on the other side. But here is the beautiful part. It leaves traveling faster than it arrived. The spacecraft essentially steals a tiny, minuscule amount of momentum from the planet. Energy is conserved, but from the spacecraft's perspective, it gained velocity for free, with no fuel burned and no engines fired. Pure physics magic. Mariner 10 used Venus in 1973 to reach Mercury, successfully becoming the first spacecraft to visit 2 planets on one mission, and the first to use the gravity assist successfully. The twin Voyager 1 and 2 probes elevated gravity assists to an art form. They launched in 1977 during a rare planetary alignment that happens only once every 176 years. Jupiter, Saturn, Uranus, and Neptune were lined up just right. This configuration allowed a spacecraft to visit all 4, using a gravity assist at each planet, handing the probe off from one giant to the next. Voyager 2 flew past Jupiter in July 1979, boosting its speed and trajectory toward Saturn. Saturn, in turn, redirected it to Uranus, and Uranus sent it hurtling toward Neptune. The probe visited 4 giant planets in 12 years. Without gravity assists, this journey would have taken decades longer and required impossibly large fuel loads. The math behind gravity assists is complex. Engineers must calculate the approach angle, altitude, velocity, and timing with extreme precision. Miss by a few miles and the maneuver fails. Arrive too fast and the planet cannot redirect you properly. Come too close and atmospheric drag destroys the spacecraft. The margin for error is razor thin. Messenger used this technique 6 times to reach Mercury, including 1 Earth flyby, 2 at Venus, and 3 at Mercury itself. Each maneuver bled off velocity slowly, allowing the probe to spiral inward over 6 years. It finally had a low enough speed to enter orbit without burning massive amounts of fuel, demonstrating that gravity assists can be used for deceleration, not just acceleration. Cassini used 4 gravity assists to reach Saturn, flying past Venus twice, then Earth, then Jupiter. The Jupiter encounter in December 2000 was critical, flinging Cassini outward with enough velocity to reach Saturn 4 years later. The probe could not have made the billion-mile trip otherwise. Gravity assists add years to mission duration, as direct trajectories are faster, but require more fuel than spacecraft can possibly carry. Mission planners must choose: arrive sooner but with less fuel for orbit insertion, or take longer, but arrive with full tanks and capability for science. This technique has become standard practice. What gravity assists taught us is profound. Space is not empty. Planets are not just obstacles, they are resources. Their motion and mass can be harnessed. Orbital mechanics is not about fighting gravity. It is about using gravity as a tool. Dance with the planets correctly, and they will throw you across the solar system. But there is one planet that has become the master key for nearly every outer solar system mission. A world whose gravity, well, is so powerful, it can fling a spacecraft anywhere it needs to go. Jupiter. This gas giant contains more mass than all other planets combined. Its gravity, well, extends millions of miles into space, and every mission to the outer planets uses Jupiter as a mandatory pit stop. Pioneer 10 arrived at Jupiter in December 1973. The encounter accelerated the probe enough to escape the solar system entirely, making Pioneer 10 humanity's first interstellar object. Jupiter made that possible. Voyager 1 reached Jupiter in March 1979. The close flyby boosted its velocity by 35,000 inches, nearly 10 miles per second gained essentially for free. The probe used that energy to reach Saturn 16 months later. Without Jupiter, Voyager 1 would still be crawling through space somewhere beyond Mars. Why is Jupiter so useful? The numbers tell the story. Jupiter orbits the Sun at 29,000 diameter. When a spacecraft approaches Jupiter from behind, traveling in the same direction, it can gain enormous velocity. The transfer of momentum from Jupiter to the tiny probe is negligible for the planet, but massive for the spacecraft. The planet's gravity well, called the Hill sphere, extends roughly 32 million miles into space. Inside this region, Jupiter's gravity dominates. Mission planners use this region like a cosmic intersection. Enter from one direction, leave going another, and almost always emerge faster than you arrived. Jupiter's radiation belts are brutal. The planet's magnetic field traps charged particles, forming radiation belts far more intense than Earth's. Electronics must be heavily shielded. Even so, the Juno probe systems are gradually degrading because the radiation slowly destroys circuits. The spacecraft has a limited lifespan because Jupiter's environment is so hostile. Future missions will continue using Jupiter. Europa Clipper, launching in 2024, will use gravity assists to reach Jupiter in 2030. It will then orbit Jupiter while flying past Europa repeatedly, aiming to study that moon's subsurface ocean. Jupiter is the essential gateway to the outer solar system. No mission to Saturn, Uranus, Neptune, or beyond skips this mandatory stop. But reaching Saturn requires even more patience. Even with Jupiter's help, the journey demands years. Saturn floats roughly 886 million miles from the Sun, and reaching its majestic rings requires a commitment measured in presidential terms. Pioneer 11 reached Saturn in September 1979 after 6 years of travel, utilizing Jupiter's gravity assist just 16 months earlier to redirect itself toward the ringed giant. Voyager 1 arrived in November 1980, 16 months after leaving Jupiter. The flyby revealed active weather systems, lightning storms bigger than Earth, and moons with bizarre features, including Titan, which had a thick nitrogen atmosphere. The Cassini mission changed everything. This massive probe launched in October 1997, carrying the Huygens lander for Titan. Cassini took 7 years to reach Saturn, arriving in July 2004. 7 years, nearly 3,000 days of cruise through space, all via an indirect path that included 2 Venus flybys, 1 Earth flyby, and the critical Jupiter assist. Orbit insertion around Saturn required extraordinary precision, The probe approached at 72,000 nm and had to fire its main engine for 96 minutes straight. This burn consumed tons of propellant, slowing the spacecraft just enough for Saturn's gravity to capture it. If the engine had failed, Cassini would have flown past and been lost forever into the cosmic dark. The mission lasted 13 years in Saturn orbit, completing 294 orbits of the giant planet. Cassini discovered subsurface oceans beneath the ice of Enceladus, a tiny moon that shoots geysers containing organic molecules into space. This tiny icy world became one of the most important discoveries in planetary science. The 7-year journey to reach Saturn represents a practical minimum using current technology. Direct trajectories take significantly longer. Cassini's path, with multiple gravity assists, was the optimized route. Engineers cannot significantly improve on this timeline without radically new propulsion. Saturn teaches us patience. Beautiful things take time to reach, demanding 7 years of waiting and 7 years of hoping the spacecraft survives the void. But Saturn is not the edge. 2 more ice giants orbit farther out, worlds so distant that only one spacecraft has ever visited them. And that journey took over a decade. Voyager 2 lifted off in August 1977 with a final destination of Neptune, which orbits 2.8 billion miles from the Sun. Expected arrival, August 1989, 12 years of travel. The entire trip took advantage of that once-in-a-lifetime planetary alignment, the Grand Tour, which will not happen again until 2153. Voyager 2 reached Jupiter in 1979 and Saturn in 1981, using each to accelerate toward the next. The probe flew past Uranus in January 1986, 8.5 years into the journey. Uranus's gravity then flung Voyager 2 toward Neptune for the final 3-year leg of the trip. Every day carried the probe farther from Earth. Communications required over 4 hours one way at light speed. If something broke, the spacecraft had to diagnose and fix itself before ground controllers could even respond. Neptune appeared as a brilliant blue world with wind speeds reaching 200 mph, the fastest winds in the entire solar system. Voyager 2 discovered Neptune's great dark spot, a storm system larger than Earth. The largest moon, Triton, became the mission's grand finale. Triton orbits Neptune backward, suggesting it was captured from the Kuiper Belt. Most shockingly, Triton has active geysers shooting nitrogen gas high into space, showing geological activity on a world that is minus 390 degrees Fahrenheit. The Neptune flyby lasted just hours. Voyager 2 could not slow down or orbit. It raced past at 38,000 nm, collecting every piece of data possible. Then, Neptune shrank to a point of light and disappeared. 12 years to reach Neptune. 12 years of waiting. The spacecraft survived and completed the Grand Tour, visiting 4 planets, discovering moons, and transmitting thousands of images. No spacecraft has visited Neptune since, and no missions are currently planned. If a probe launched today, it would arrive in the late 2030s, over a decade away. The journey taught engineers what is possible. 12 years is a long time, but not impossible. Humans age, but spacecraft do not. The Voyagers proved that machines can survive decades in space and operate far beyond their design specifications. But Voyager 2 used a shortcut that is no longer available. Future Neptune missions must take longer routes or use fundamentally new propulsion, because chemical rockets have reached their absolute limits in the outer solar system. The entire solar system is defined by movement, which is the true challenge of travel. Earth orbits the Sun at 67,000 nm. Mars orbits at 54,000 nm. Jupiter moves at 29,000 nm. These are not straight lines, they are curved, elliptical orbits. When you launch from Earth, you inherit Earth's orbital velocity. You're already moving 67,000 points around the Sun before your rocket even fires. To reach another planet, you must change your orbit. You need to curve your trajectory from Earth's path to intersect the target planet's orbit, and you must time the intersection so the planet is actually there when you arrive. Miss the timing, and you fly through empty space while the planet is somewhere else. This is called a Hohmann transfer orbit, the most fuel-efficient way to travel between two circular orbits. The spacecraft fires its engines to enter an elliptical path. One end touches Earth's orbit, and the other touches the target planet's orbit. The spacecraft then coasts along this ellipse. When it reaches the target orbit, it must fire its engines again to match the planet's velocity. Hohmann transfers take time. To reach Mars takes roughly 8 months. To reach Jupiter takes years. These durations are fixed by the unforgiving mathematics of orbital mechanics. You cannot speed them up without burning vastly more fuel, and spacecraft can only carry so much propellant. Direct trajectories exist, where you point straight at Mars and fly there, but they are impractical. This requires constant thrust to fight the Sun's gravity. Chemical rockets cannot sustain thrust for months. They burn all their fuel in minutes. Ion drives can thrust continuously, but they produce a tiny, almost imperceptible acceleration. Even with these, the trip still takes months or years. The Sun dominates everything. Its gravity well is enormous, and spacecraft are constantly falling toward it while traveling between planets. Trajectories must account for this constant gravitational pull, balanced against spacecraft velocity. One mistake, and the probe flies off course. Course corrections require precious fuel, which is limited, meaning every maneuver must be perfect. Launch windows compound the problem. Earth and Mars align properly every 26 months, but Jupiter aligns less frequently, and Saturn even less often. Miss your launch window, and you must wait years for another chance. Some missions wait decades for an optimal alignment. Voyager's Grand Tour used an alignment that happens once every 176 years. Launch windows exist because the planets orbit at different speeds. Earth completes one orbit every 365 days, while Mars takes 687 days. They align favorably every 780 days, or slightly over 2 years. During optimal alignment, Earth and Mars are on the same side of the Sun, minimizing the distance. A spacecraft can travel a Hohmann transfer orbit efficiently, with reasonable fuel requirements and acceptable travel time. Launch 6 months later, when the planets are poorly aligned, and the trip becomes much harder. Mars might be on the opposite side of the Sun from Earth. The spacecraft must travel much farther, fuel requirements skyrocket, and travel time doubles or triples. Most missions become impractical. The tyranny of launch windows shapes all mission planning. You cannot explore Mars whenever you want. You must wait for alignment. You cannot visit Jupiter on a whim. The planets dictate the schedule, and humans must be patient. We cannot command the solar system. We must work within its rhythms. But even if you launch at the perfect moment, the journey requires technology, and chemical rockets hit their theoretical limits decades ago. Every spacecraft currently exploring the solar system uses chemical propulsion, the same basic technology that launched Apollo to the moon. We have refined it, making it more efficient, but we cannot escape its fundamental limitations. Chemical rockets work by burning fuel and oxidizer together. The reaction produces a hot gas that exits through a nozzle at high velocity. Newton's third law of motion dictates that gas goes backward, and the rocket goes forward. The exhaust velocity determines efficiency. Chemical rockets expel gas at roughly 9,000 to 15,000 Nm. This is called specific impulse, and it measures how much thrust you get per unit of propellant. These numbers have barely changed in 50 years. The problem is the unforgiving rocket equation. Rocket velocity cannot exceed exhaust velocity without staging or gravity assists. As you burn fuel, the spacecraft gets lighter, which allows acceleration, but eventually you run out of fuel. Maximum velocity is severely limited by exhaust speed and mass ratios. New Horizons left Earth at 36,000 km, requiring a massive Atlas V rocket. Most of the launch mass was fuel. By the time the spacecraft separated, almost all the propellant was gone, and the probe coasted the rest of the way. Chemical rockets must carry their propellant. This creates a vicious cycle. More fuel means more mass, and more mass requires exponentially more fuel to accelerate. Eventually, the rocket becomes impractically large. Sending a mere 10 tons to Neptune or Pluto requires creative staging and massive gravity assists. We are trapped by the chemistry of molecular bonds, which store only so much energy. Ion drives offer a theoretical solution by accelerating ions to much higher velocities, with exhaust speeds reaching 60,000 to 100,000 nm. This is 10 times better than chemical rockets. But ion drives produce tiny thrust, with acceleration measured in millimeters per second squared. They must run continuously for months or years. The Dawn spacecraft used ion propulsion to visit Vesta and Ceres. The mission took years because Dawn accelerated slowly but continuously, accumulating velocity over time. It achieved more total velocity change than any chemical rocket could manage. But the journey was slow and patient. Ion drives cannot launch from Earth, as their thrust is too weak to overcome gravity. But in deep space, where no air resistance exists, gentle, continuous thrust is powerful. The Mercury mission, Messenger, proved that patience and complex trajectories still work, despite the challenges. The 6.5-year journey was the ultimate example of overcoming the sun's gravity problem through extreme patience and gravity assists. Messenger could not simply stop at Mercury. It would have needed fuel tanks bigger than the spacecraft itself to decelerate from the speed it gained falling toward the sun. Engineers chose the only possible approach, 6 planet encounters to gradually bleed off velocity over years. The spacecraft spiraled inward, painfully slow, before finally entering orbit. The Bepi-Colombo mission is currently repeating this process. The European and Japanese probe launched in 2018 and will not reach Mercury orbit until December 2025, a 7-year wait. The 9 planetary encounters, 1 Earth, 2 Venus, 6 Mercury, are all calculated to break the spacecraft without burning massive amounts of fuel. This technique made Mercury reachable, but at the cost of years. But first, we must understand why faster travel is not just about convenience. It is about survival. Why cutting months off trips saves lives. Why radiation is the invisible killer stalking every deep space mission. Space is trying to kill you every second you are in the void, not from a lack of air or cold, but from invisible particles moving near the speed of light that tear through your cells. Cosmic rays are atomic nuclei stripped of electrons. They originate from supernovae, neutron stars, and black holes, and they cross the galaxy at relativistic speeds. When they hit human tissue, they shatter DNA, create free radicals, and cause mutations, cancer, and acute radiation sickness. Earth's magnetic field and atmosphere deflect most cosmic rays, protecting us within a planetary bubble. Step outside that bubble, and radiation exposure increases 100-fold. A round trip to Mars takes roughly 18 months. Astronauts would absorb dangerous radiation doses during the journey, significantly increasing their cancer risk. NASA limits an astronaut's career exposure to 1 sievert, and a single Mars mission approaches 60% of that lifetime limit. The immediate threat is solar particle events. Coronal mass ejections spray charged particles into space. If astronauts are caught in open space during a major solar event, they could receive lethal doses in hours, leading to acute radiation sickness and death within days. Spacecraft shielding helps, but only partially. Aluminum, for instance, can stop some radiation, but it creates secondary particles when cosmic rays strike the hull. And these secondary particles can be more dangerous than the originals. The simplest solution is speed. Shorter trips reduce exposure proportionally. Cut travel time in half, and the radiation dose drops in half. This is why propulsion advances are not optional. They are a matter of survival. Nuclear thermal propulsion could reduce the Mars journey to 3 months instead of 7. That cuts radiation exposure by more than half. Shorter trips also reduce other risks. Microgravity causes bone loss, muscle atrophy, and damage to vision and cardiovascular systems. Faster trips minimize these effects. Psychological factors, such as isolation and confinement, also accumulate. Shorter missions mean crews spend less time in hostile environments, improving mental health and keeping performance sharp. Chemical rockets simply cannot safely carry humans beyond Mars. The journey times are too long, and the radiation exposure is too high. Nuclear propulsion offers the solution. It is necessary to cut travel time by factors of 2 to 5 and make deep space accessible. Nuclear thermal propulsion uses nuclear fission to generate heat. A reactor heats liquid hydrogen to extreme temperatures. The hydrogen expands and shoots through a nozzle, reaching an exhaust velocity of 15,000 knots to 20,000 mph. This is double what chemical rockets achieve, meaning double the efficiency, half the fuel mass, and much faster trips. The concept is not new. Between 1955 and 1973, NASA and national laboratories built and tested 20 nuclear thermal rocket engines, and they worked. They produced incredible thrust, achieving 3 times the performance of chemical systems. Those early programs used weapons-grade fuel, which created unacceptable proliferation risks. However, modern designs use low-enriched uranium that cannot be weaponized, and safety is prioritized. The reactor remains inactive during launch and only turns on once the spacecraft is safely in orbit. If the rocket crashes on the launch pad, radioactive material stays contained. Once activated in space, the reactor fires and the fission releases energy, heating the hydrogen propellant to 4,400 degrees Fahrenheit. A nuclear thermal rocket could accelerate a Mars-bound spacecraft to much higher velocities than chemical systems. The journey could shrink to 6 weeks instead of 7 months. Astronauts spend less time in radiation, less time in microgravity, and less time psychologically isolated. Everything improves. The Draco program aims to demonstrate this technology by 2027. This project will launch a nuclear thermal rocket, test it in orbit, prove the concept works, and show the public that nuclear propulsion is safe. If Draco succeeds, operational systems could fly by the mid-2030s. Mars missions would use nuclear thermal propulsion, with journey times cut in half or better. Beyond Mars, this technology enables missions impossible with current chemical systems. Nuclear electric propulsion offers even better efficiency. Instead of heating propellant directly, the reactor generates electricity to power ion drives. The reactor's heat drives a turbine, generating electricity that continuously runs the ion drives. The xenon gas is ionized and accelerated to extreme velocities, reaching 100,000 mile exhaust speed. This is 10 times better than chemical rockets. NASA estimates nuclear electric propulsion could reduce a Mars round trip to roughly 2 years total. The spacecraft would accelerate continuously for weeks, coast briefly, and then decelerate into Mars orbit, offering flexibility and abort options throughout the journey. The power comes from a nuclear reactor, providing constant energy regardless of distance from the sun. However, the major engineering challenge is heat rejection. Space reactors have no air or water for cooling. Heat must radiate into space, requiring enormous radiators, arrays the size of football fields. Future plans include launching pieces separately and assembling the large radiators in orbit. This approach unlocks possibilities, as spacecraft are no longer limited by the rocket fairing size. The ultimate limit to all these systems, whether nuclear thermal or nuclear electric, is hydrogen. Liquid hydrogen is the best rocket propellant. It has the highest energy per kilogram and the lowest molecular weight, providing the maximum exhaust velocity when heated. However, hydrogen liquefies at -423 degrees Fahrenheit, just 37 degrees above absolute zero. Storing liquid at these temperatures is brutally difficult. Boil-off is the killer. Heat leaks through the insulation, and the liquid hydrogen absorbs that heat, causing it to vaporize. Pressure builds in the tank, and vents must release the gas, leading to propellant loss. Long missions lose significant fractions of their hydrogen. Nuclear thermal rockets need hydrogen for propulsion. Losing fuel to boil off makes the missions impractical. Engineers are developing zero boil-off storage systems that capture evaporated hydrogen, compress it, reliquefy it, and return it to the tank. The temperature jump required for nuclear thermal is enormous, from -420 degrees to +400 degrees. Managing this gradient requires extraordinary engineering, particularly for the pumps, which must move liquid hydrogen from cryogenic storage into the hot reactor. If hydrogen storage proves impractical, nuclear thermal propulsion might be forced to use less efficient propellants like methane, which liquefies at a warmer -260 degrees. But even if we solve hydrogen storage and perfect nuclear propulsion, the fantasy of light-speed travel remains just that, a fantasy. Light travels at 186,000 miles per second. Nothing moves faster. This is the universe's absolute speed limit, as set by Einstein's physics. At light speed, Mars is 3 minutes away. Jupiter is 35 minutes away. Neptune is 4 hours away. The entire solar system shrinks to a day trip. However, light speed is impossible for massive objects. As objects accelerate, their mass increases. Approaching light speed, mass approaches infinity. Infinite mass requires infinite energy to accelerate further. The universe does not contain infinite energy. The barrier is absolute. Even reaching 10% of light speed requires unimaginable amounts of energy. The fastest human-made object is the Parker Solar Probe, which reached 430,000 diameters. This is 1/16th of 1% of light speed, pathetically slow compared to photons, yet incredibly fast by human standards. Interstellar travel requires relativistic speeds. Even at 1% of light speed, reaching the nearest star takes 400 years. These journeys exceed human lifetimes and exceed political stability timescales. What if we could accelerate constantly? Imagine a spacecraft that accelerates at one full gravity, 9.8 meters per second squared, the same force you feel standing on Earth. Physics says this ship could reach Venus in 35 hours, Mars in 41 hours, Jupiter in 6 days, and Neptune in 16 days. The spacecraft would accelerate for half the journey, then flip around and decelerate for the second half. arriving at the destination with zero velocity relative to the target. The catch is obvious. Maintaining one gravity of acceleration requires truly enormous energy. Chemical rockets burn out in minutes. Nuclear thermal might sustain thrust for tens of minutes. Ion drives produce 1/110,000th of one gravity. To achieve a constant one gravity of thrust to Mars, the ship would have to be 99% fuel. The one-gravity ship remains theoretical, a thought experiment, showing what becomes possible with sufficient propulsion. That sufficient propulsion does not exist. Fusion propulsion might manage it, using hydrogen fusion to sustain thrust for hours or days. But fusion reactors are still experimental on the ground, let alone in space. Partial gravity might be achievable sooner. 1/10 of a gravity of acceleration is 10 times what ion drives produce. At this acceleration, Mars requires 9 days instead of 41 hours, still dramatically faster than current missions. Advanced nuclear electric propulsion might approach this. However, there is a limit to human endurance. Even if we could generate arbitrary thrust, our bodies have a breaking point. 3 gravities of sustained acceleration, where your body feels 3 times heavier, would cause serious medical problems. Your arms would be too heavy to lift. Blood would pool in your legs. Your heart would struggle to pump blood to your brain. Vision would narrow. Extended exposure to 3 gravities would damage the body, compressing vertebrae and causing organs to sag. A 3-gravity Mars mission would theoretically reach Mars in 24 hours. But the astronauts would arrive incapacitated, possibly unconscious, and definitely suffering physical damage. The speed advantage is worthless if the crew arrives injured or dead. The sweet spot for human missions is probably 1 to 1.5 gravities. Uncomfortable, but manageable. This acceleration range provides significant speed benefits while remaining within human tolerance. But this speed still requires nuclear systems, which are only just now reaching demonstration phase. Ultimately, the travel times to each planet are not just statistics. They are the boundaries of human expansion, the limits that define what is possible. Current technology restricts us to the inner solar system. Nuclear propulsion is not optional. If we want to expand beyond Earth, it is mandatory. Chemical rockets cannot build an interplanetary civilization. Nuclear systems might. Fusion propulsion would accelerate expansion dramatically, making the outer solar system accessible and its resources unlimited. The decisions we make in the next few decades matter. Investing in propulsion technology today enables expansion tomorrow. Failing to invest traps us on Earth, leaving us vulnerable and limiting our potential. The travel times we accept determine our future. We know how long it takes to reach each planet with current limits, but we are actively working to change those numbers. If this changed how you see interplanetary travel, watch this next video on the long-term viability of nuclear thermal propulsion for colonization to keep the story going.